My name is Elachi Mamadou Sonko from the University of Dhaka. I have a master in environmental sciences and completing a PhD in these fields. And also I am freelance consultant in sanitation issues since 2012. And I have a lecture position at the university since 2011. So we have today I am here to moderate this session, the second session of Postal Lightning, and with this session we have 7 presentations because one presenter is going back to home and she jumped in this session. So we are going to present the first presenter, who is from the University of Berkeley. I just want to precise that you have 5 minutes to present your results and to be in the time. So let me present you Emily Wood from the University of Berkeley.
Great. And I apologize again for jumping in. I have a plane flight out in a couple hours. So like I said, my name is Emily Woods. I'm with Sanovation. Sanovation is a small startup in Kenya. We work with Andrew Foote and Hannah Lopi, who are still back in Kenya working. What we're going to be talking about today is a reuse option for feces, looking at feces charcoal, which is what we've been making in Kenya. So this kind of our 2 places where we've been working. This past year we've been up in Kakuma, working with UNHCR and CDC on a pilot with about 300 refugees there. But we're normally based in Naivasha, which is a small town a couple hours north of Nairobi. It's mainly a peri-urban setup there on the lake. We're currently at 50 households subscribing to us, so I'm kind of explaining a little bit of our model and what we're doing. It's exciting for us. We've been running our operations full-time there since August, about 100% attention rate for our customers. It's really going to start expanding. But what we are going to be focusing on as much as possible, I think there's a is the fact of these briquettes that we've been making out of feces. So this is kind of how our Sanovation model works. It starts first with a monthly subscription for about $7 a month. We actually provide people an in-home dry toilet. It's urine diverting, and with that comes twice a week feces collection and urine collection. We then treat it using solar thermal, and then the third part here is what we've just been figuring out in the past year. For the longest time, we knew we could collect it, we knew we could treat it, but we weren't sure what to do at the end. And so that's mainly what we're going to be focusing about today. So just kind of a quick overview. These are our toilets. We call them chopoas. They're based a lot off of soil and resources toilets that they use down in Haiti. And they are wooden based, they do urine diverting, and they've got the buckets on the inside that collect the feces and then also the urine. Sometimes they're transported by cart, sometimes by motorcycle. That's actually my motorcycle. It's really fun that you can deliver these toilets and pick up poop on the same bike. And so that's $7 a month, twice a week collection. So then these buckets are then taken to these big solar parabolic mirrors where we do solar thermal, where some of our work with CDC proved over 4 log inactivation in just a few hours, so getting about 65 degrees Celsius inside these black metal drums. And so this specifically was our setup up in Kakuma. So for 300 refugees, we had 300 different parabolas. Each of those parabolas costs about $200, and we can treat about 100 people's waste continually off of that. So that's why we have 3 here. You can kind of see some of our E. coli data that we did there in CDC. But like I said, the point of today is actually what then. So at this point, what we realized in Naivasha is everyone kept asking us with these big mirrors, like, can we cook on it? Like, no, we're not cooking on it, we're cooking shit. And they're like, but that's really what they needed. They needed feces, they needed a fuel that they can use because charcoal is so expensive. And so what we realized is that while we're not only treating the feces, we're also reducing the moisture down to about 30 to 40%. And so it had a high calorific value, and at the same time, it also has that naturally sticky, hard drying properties that feces has. So we realized that it made a really great binder. So in Naivasha, where we work, there's all these rose farms. And all these rose farms have all this leftover biomass. So we started collecting that rose waste for free, carbonizing it, grinding it up, and we use that, and then use the feces as the binder. So this is just kind of our mixture here. So that we mix it, and then we pressed it into these materials, and that's kind of what I got here. We call it Macadamia. And you can kind of see the calorific value, or a little bit less than local charcoal, but better than just wood. And what we found is that it's less instantaneous heat, but over longer amounts of time. So it's actually really great for cooking your beans, your corn, your potatoes, not necessarily the best for boiling water. Our CO emissions are a lot less than local charcoal, so about 1/3, so it's still at 60 parts per million, which is not really what you want for indoor cooking, but a lot better than the other option. We're also not only saving a lot of trees, but it's a lot cheaper. So I think the number one reason why people like this is about 1/3 of the price of charcoal. Local charcoal in Kenya has multiplied 6-fold in the past 10 years, so it's astronomical. So it costs us about $70 a ton to make it, and it's sold about $170, that's our profit margin, compared with local charcoal, which is usually sold for about $600 per ton. So it adds up fast. People always ask us what other people think of it. People like it. They like it because it's cheaper. They like it because it's less monoxide. And it even passed a taste test. A guy up in Kakuma not only licked it, he ate one for us, and he said it didn't have a taste. So that's good. We had everyone use it, kind of look at these different parameters and a few others, and compare it against charcoal, compare it with ours, the Macadamia that's ours, and then other briquettes that are made locally. And we're doing quite well. So our idea is that we're reusing feces and we're coming out at least comparable to local charcoal. It's working well for us. So that is a very quick overview of what we do. We have any questions now? Or? Okay, wonderful. I'm going to leave the charcoal here if you don't want to see it.
We have to present. We have to leave official because we have to leave. We have not enough time to do face-to-face questions. So the second one is from the Department of Environmental Health and Science and Technology, Jima from Ethiopia. I want to introduce Adele Bayeni. Good afternoon, everybody.
So I'm going to present on status of urban sanitation in the capital of Ethiopia and the urgency of adopting integrated fecal sludge management. These are the contributors. Next slide, please. Next slide. Okay, as an introduction, 60% of the disease burden is related to poor sanitation. You can imagine the public health significance of sanitation and what is the current state of sanitation and indicators used to monitor in urban sanitation. Based on the definition of Joint Monitoring Program or WHO and UNICEF, feces and urine should go to improved sanitation technology, and this improved sanitation technology should be used properly, should be properly utilized, and then the fecal sludge, there should be complete chain of fecal sludge management. If there is access to improved sanitation in such a way, we can say that there is pollution control and promotion of public health. Otherwise, the presence of sanitation technology alone will not bring change to public health and prevent pollution. Next slide. So the objective of this research is to investigate the current state of sanitation in Addis and also to map trends of sanitation in urban areas and to determine the chain of fecal sludge management system with current practice. Yes. So the data includes a cross-sectional survey conducted in 5 subsidies. In 5 subsidies, and also a national inventory of result of 2014 conducted by the government, national government, and also a sample survey conducted by Central Statistical Authority of Ethiopia. Next slide, please. So the result, the current state of access to improved sanitation in the capital city, 88.6% of the population in urban slums have no access to improved sanitation. 95.5% of the national population has no access to improved sanitation, and the national sanitation urban coverage is only 17.5. And when we see the trend of access to improved sanitation in the capital city, which are in red, it is gradually declining. And the recent survey showed that the access to improved sanitation is about 40%. And when we see the national urban sanitation coverage, it is also declining when we compare the access to sanitation in 2014 and in 2004. So when we see the user behavior and feeding time practice in Addis, 95% of the toilets were not clean, and 88% of the households use municipal feeding time. So private feeding time is almost nil. It's about 7.8%. It's not 7.8% of the households release their fecal sludge directly to water boards, and 4.2% use private feeding time. And because of the limited access to feeding time, 50% of the toilets were full, and the residents are forced to use full toilets, as you can see from this photo. When we see the fecal sludge management system in the capital city, the chain of fecal sludge management, the containment, mainly dry toilets, in Addis 75%, and in urban slums 90.8%. And the final fecal sludge, the partially treated and untreated fecal sludge, is disposed to land and water. Resource recovery oriented fecal sludge management is almost nil. So when we see the chain of fecal sludge management, as I have said, the containment is mainly dry toilets. Flush toilet is only less than 5%, and septic tank is also less than 5%. So most of the urban residents use dry toilets. And the final disposal of both untreated and treated toilet is to land and water. So in conclusion, current access to improved sanitation is far from the MDG target, regardless of several reports of WHO and other NGOs. Declining trend to access to sanitation, this might be because of the population growth and the increasing demand in sanitation. Safe and resource recovery oriented fecal sludge management is merely absent in the city. That shows the urgency of adopting resource recovery oriented fecal sludge management in Addis. Finally, I just read it in the news why Bill Gates bring people. He understands that sanitation solution should be all in one, and it should be in closed loop approach. Thank you.
Thank you, Alve. I now introducing Ishale Dalesha from the same University of Minsk from Ethiopia.
We are not from the same university. I'm from Aberdeen University, and a bit safe. I'm far away. I'm in 505 kilometers far away from the capital city. I'm going to present one of the other research we had in the Clara project. So these are contributors during the research work. So I will go through the slides. So just to have information about the location of the urban beach city, I mean town, and then the university itself is somewhere 505 kilometers away at the southern part of the nation, and with around 100,000 population, and it is very urban. So to start from the background for this research work, so we had a Rosa project and SPA and Clara project. And in three of these projects, we tried to pilot and demonstrate a resource-oriented sanitation system in Arabia. So due to this, we had a kind of a big challenge in a huge volume of urine, and also we had also a kind of solution we said to work with the local SMEs, small and micro enterprises. So due to this background, and then the problems we have, like a local challenge and the global challenge. The local challenge are challenges related to the way how we handle these contexts from diverted dry toilets, and then the phosphorus insecurity that is coming very soon. So therefore, for this, as a measure, it's not working. I don't have time. It's not working. Okay, so as an objective, we plan to precipitate provide and to see the feasibility in case of economic analysis, and also we have checked how the performance is compared to the chemical fertilizer and so on. So to attain this objective, we have specific objectives like the quality analysis, the stored urine quality analysis, along with the fresh one, and also the process efficiency check, and growth and yield comparatively with the control with chemical fertilizer and also struvite. So finally, I've checked the feasibility situation. Shall I direct it to Zoom? So to see the experiment, how we conducted, so you can see we have selected crop maize to have like a yield within a short time, like 3 months. Then DAP and urea, struvite, and little effluent, and control without any of this organic or chemical fertilizer. So triplicates are used, that means 3 for each, in total 9. So you can see this is the overall process of our experiment. So we started, the overall process. So we started from collection. As I've said, we have already urine diverted dry toilets in our permit. So therefore, we made like collection. Please, collection. I'm here at stage 1. Collection. So the collection is conducted by the groups, like solid waste collecting group in the town. They bring this urine and feces down to the experiment site. So it can be temporarily stored at the same site, and then we take a sample from the urine storage, and then we analyze the stored urine quality. So therefore, then the next step is like precipitating struvite based on the molarity ratio. We have tried so many ratios to have good efficiency improvement. So therefore, so finally this is tried on the 3 triplicates. From the result you can see, the struvite result and then the chemical fertilizer is quite comparable in both growth and yield. So the way we tried up this struvite is like open air trial. And then we have like information about the NPK value, and then so this helps us to calculate the nutrient-based cost analysis. that's to come. So let's go. So the efficiency case is like we use the local material, but we conducted, I mean, we adapted the provided reactor from Iran. I really like to say thank you, Iran guys, they are available here. So we adapted the design with the same volume and capacity, but the only change is the filter material, that's local, because we want this to adapt, I mean, to the local situation that SMEs can run this by themselves. This is the original stuff. So therefore, the efficiency like 7 point something, but it looks really low compared to some values we have seen in the literature from Iraq. Having said this one, I have some conclusion over here. So the first one is to maximize this efficiency situation, additional efficiency has to be updated somehow. So because it looks low compared to literature values. And crop tracks show a similar fertilizing effect of chemical fertilizer and herbicide, an important indicator for farmers to convince. And herbicide application is currently not yet economically feasible due to the local situation we have. But this analysis is made only based on nutrient value. We didn't consider the environmental issues that something attached to this ecological kind of view. So therefore, in that case, we can say that economically not feasible in our situation in Arabid. So the future research should be very important, and also the government has to closely monitor this chemical fertilizer findings. So this is my conclusion. I really want to say thank you for generous financial support from the European Commission, the Book University, very efficient coordinating university, the CLARA team in general, individuals and organizations. You can have the detail in this site. Thank you very much.
The fourth presenter is from the University of KwaZulu-Natal. I want to introduce Simon Lawrence, civil engineer, working as a consulting with authority position of the University of KwaZulu-Natal.
Thank you, Mr. Chair. Ladies and gentlemen, pit latrines do not cause water pollution. Clearly, the retort for that is, well, it depends. And to get more information on when and how it depends, I refer you to my co-authors. I'm just here to advertise, particularly Bruce Wickham, who's done all the hard work in this. Yes, of course, it depends. It depends on the type and the use of the pit latrine, the soils and the geology and the climate. Our research was done in the eastern side of South Africa, where we have 100 millimeters per annum of rain, which occurs predominantly in the summer in the form of subtropical thunderstorms. The rest of the time it's dry. So what we aim to do is define the processes of how the nutrients and pathogens move from pit latrines and porphyry systems, and then perhaps learn on how this can be applied to other soils and geologies and climates, and define guidelines for safe distances. We put together a research which combined defining the characterization of the area with hydrogeology surveys, near-surface geophysics, and a lot of monitoring both of nutrients, pathogens, and other traces such as stable isotopes of water, etc. We discovered that the interface between the soil and the bedrock is very dominant in where water might interface with the pit latrine, and this predominantly in high rainfall events. So what we found is a very consistent occurrence of nutrients and pathogens at least up to 3 meters away from the pits. The pits down at bottom of slopes, clearly more predominant. And then intermittent after high rainfall events, we find nutrients and pathogens reaching a distance of 60 meters and possibly into the stream. But in those occasions, the stream flow is fairly high because of the rainfall event, and so concentration-wise, no great significance to the water resource. But significantly, our findings show that near-surface lateral flow can move nutrients and pathogens very quickly on intermittent occasions. And so if you'd like some more detail, we're welcome you to our website.
Thank you, Simon. You have given us 1 more minute, so I want to thank you about that. The next presenter is from the Department of Technology of the Swedish University of Agricultural Science. I want to introduce Annika Nordin.
Thank you for that introduction. I'm going to tell you about a project, a joint project between my home university, 4 municipalities, and the Federation of Swedish Farmers that aims to achieve the Swedish national environmental goals to reuse nutrient from toilet waste. So there's quite a lot done on ammonia sanitation in the lab scale. So this project aims to investigate how to perform this in the full scale and optimize the treatment. So slurry manure tanks at farm sites that have been abandoned due to change in agricultural practice is used as storage tanks during the treatment, but they need to be covered, so that is an investment that has to be made. But otherwise, this infrastructure could be used. And in this particular trial that I'm going to present, 1% of urea was added to give ammonia to sanitize the fecal waste. And it's a full-scale trial, though it's on the pilot state. So it was a 1,000 cubic meter manure tank that was used. And this fecal sludge that was treated came from molding tanks that source separated this toilet waste with flush water, so it was quite diluted. And different aspects were investigated, like how to mix and how to add urea, what temperatures do you get, is it difference, is there a temperature gradient in the material, and along with organizational aspects and cost. But this, what I present, focus on the sanitization. So this is an overview of the management of filling the fecal sludge into the tank, and one of the aims was to study if the filling action itself could mix in the urea. So urea was added, part of it initially, into this screening pump station to see if that could be enough to get a homogeneous material. And the tank was filled up, and when it was reaching its final volume of fecal sludge, then the final dose of urea was added to reach this targeted 1%. And you see also in this diagram that initially then the urea concentration ranged from 2.5 to 0.5 during the period of filling and until the final adjustment. And the temperature ranged from 15 to almost 20 degrees. And it differed in between for the different heat in the tanks. So the organisms, we used indicator organisms due to the lack of pathogens in this sludge and doing it in the field. So we didn't want to add any pathogenic organisms. So we started to study already during the filling. So you can see that the thermotolerant coliforms, which is constituted mainly by E. coli, that they were inactivated at the first sampling down to detection limits where they re-emerged with the filling. Both Ephemerophages and thermotolerant coliform bacteria was inactivated rather fast, whereas somatic coliphages and enterococci had a slower trend of decrease. However, the enterococci, its value as an indicator for ammonia sensitization is under discussion. So, some conclusions from this is that after 2 months from the addition of the urea, this material was considered safe to use for crops not intended to be consumed raw. But it was also quite a stratification that the ammonia concentration was much higher in the bottom compared to the middle and the top samples. So active mixing is recommended. And environmental analysis show that compared to conventional treatment in sewage treatment plant with no reuse, the primary energy used and the global warming potential was better in this system. And organization driving forces indicated that all stakeholders involved have their own driving forces, so it seemed to be a promising win-win solution. Thank you.
Thank you, Anika. Now I'm going to introduce my friend from Cameroon, Wilfried Arsenleta, from the Department of Plant Biology, Wastewater Research Group, the University of Yaoundé.
Thank you, Mr. Moderator, for giving the floor. My name is Leta Wilfried, coming from the University of Yaoundé, Cameroon. And it is a pleasure to me to share with you part of the result of my research out in Cameroon. This research was assessed on the effect of the depth and sanitation tap on the quality of fecal sludge in the Yaoundé. So, fecal management is a good challenge in low-income country where a large part of the population are related to concerned sanitation system for expected disposal. And the fecal sludge management chain include storage, collection, transportation, treatment, and or reuse. Many studies were carried out on the aspect of characterization of fecal sludge, and then the collection, treatment, and reuse. Very few studies were assessed on the effect of storage system on the quality of fecal sludge. So this study was aimed to assess the effect of the type of sanitation system and the different depth on the quality of fecal sludge. The study was carried out in Yaoundé. Yaoundé is a politic capital of Cameroon, with so, political capital of Cameroon with 2.5 million inhabitants, with a population growth rate of 2.4 percent per year. And then, the methodology of this study takes into account the two phases, the fecal sludge sampling on the field and the characterization in the laboratory. So, for the collection of fecal sludge, samples were taken in different locations of the town, and the sampling criteria was the type of sanitation facility, the location of the facility, the age of the facility. And then, characterization of the lab include physical-chemical aspect. And the characterization was done according to standard protocol. And data analysis were also done by using ECLStat software 2014, and the Fisher tests were used to assess the effect of different factors on the quality of fecal sludge. Use of principal content analysis was also used to assess the quality of fecal sludge. A part of result obtained for these research, looking the depth of the device on the nitrogen fecal sludge, we realized that in Yaoundé, lacking depth range between 0.5 and 7 meters. And then we observed that there was no significant difference or correlation between the depth of the latrine and the nitrogen content. And looking at the effect of the device of organic content, we observed that traditional latrine, PIP latrine, flush latrine, and Canon equipment latrine were showing high strength sludge. Our fecal sludge from septic tanks were record low value of organic content. Looking the physicochemical assessment and the quality of fecal sludge using principal content analysis, we observed that fecal sludge, generally fecal sludge of the storage area, were characterized by the solid fraction and organic fraction. Now, to conclude, we can say that fecal sludge characteristics in the Yaoundé town were not affected by the depth of the sanitation system, and then the septic tank were associated for the highest mineralization of fecal sludge. So I would like to thank the Bill and Melinda Gates Foundation to permit me to present this word here. Thank you.
Thank you, Richard. Now I'm going to introduce our last poster presenter, who is William Tabe from the University of Bath.
Good afternoon, everyone. My name is William Turkey. I work with Karen Nelson in environmental engineering at Berkeley in the United States. And today I'll be talking about some preliminary data from two different novel technologies, ion exchange and electrochemical systems for nitrogen recovery from source-separated urine. So our motivation starts from this graph. We're looking at the macronutrients present in waste and the amount that's excreted per person per day. The vast majority of these are present in urine. And we focus on nitrogen and extracting it as ammonia, particularly nitrogen because it has the highest amount present in urine. And we're looking to create fertilizers or disinfectants as value-added products from this urine, either fertilizers for sale or disinfectants for sale or to use in disinfecting feces. And so our problem parameters looking at this are threefold. So we're looking for dependable, efficient recovery of nitrogen, being able to be scaled in urban settings, and minimal behavior change for toilet users. So the first technology, here's a schematic of how we envision it, with a source separating toilet shown here, and a urine tank for storage. And so an ion exchange cartridge with a resin that absorbs ammonium onto it, such that urine with ammonium comes in, the ammonium stays on the cartridge, and urine without ammonium leaves the system. And then the resin can be further processed to create either a liquid fertilizer or use the resin as a solid fertilizer. And so our process so far has been to do this on two different matrices. So first, a very simple ammonium chloride solution in the lab. Second, some competition using ammonium, potassium, and sodium chloride, because those are the three primary cations present in urine. And then we hope to move on soon in the next few months to real urine with added complications like COD and dissolved organic matter. The second technology, this is complicated, but we can talk about it more at the poster. is electrochemical stripping. And the idea here is the same. It's to extract this ammonium that's present in urine. We extract it across two different membranes to then capture it separate from the rest of the urine. And here we're using an electrical impulse here with the transport of electrons, which are negatively charged. And that solicits a transport of cations like protons and ammonium across this cation exchange membrane. And then we separate the aqueous ammonia across the second membrane. And again, we're looking at this with ammonium solutions, synthetic urines, and real urine. And there's some cosmetic details in the anions, but that's the main idea there. And so our main focus here is to compare these technologies to conventional fertilizer. And so far from our preliminary analyses, we see that these are cost competitive. So looking at, this is the first technology, the second, and this is conventional fertilizer. And this has been done for the Nairobi, Kenya case because that's where our field work is. And the y-axis of this graph is the cost in US dollars per kilogram of nitrogen that's present in each of these. And so we see that right now we're cost competitive, and that's encouraging us to continue on in our studies. And so just some preliminary conclusions in future work. We're using the lab data that we've gotten from these ammonia solutions that are proxies for urine and some secondary market data. And we've concluded from the previous graph that right now it looks like electrochemical stripping is slightly more cost competitive than ion exchange, but they're both still worth exploring. And so our future work is looking at more realistic urine solutions over the next few months, looking at how the systems perform in the field in Nairobi, Kenya this summer, and then also looking at other ways of assessing these technologies, including market analyses and looking at life cycle impacts. Thank you.
Yeah, you are done. Thank you, William. Now we have 5 minutes for panel discussion because we have to leave to end this session at 15 to 3. So we have almost 5 minutes. I want to invite all the presenters to come in front of the audience and they can answer to the question. Questions? No question?
So, hi, I'm Rick from Switzerland. So my question goes to William. So I was just wondering if, even though like phosphate concentration is way lower in urine, can you combine this ion exchange, or can you use this ion exchange to also capture like phosphate in urine?
Next question. Okay, for the question. Next question. Next question, please.
Thank you very much for the presenters. My name is Daniel Hakim from the Egypt Development Bank, and I'm very impressed with presentations, particularly on the innovations regarding the end users. And my question is, if we want to scale up these operations, I mean, this is a question particularly for Emily, Annika, and William. Have you looked at the various options in which your ideas can be scaled up further in terms of looking at the stakeholders, the institutional environments, and also business aspects? Thank you very much.
Other question?
Thank you for your presentations. My question was that people talked about surveyed. I'm looking at the end product after you've precipitated out that nitrogen, what happens in manufacturing, and what, in terms of kilograms, like what are we looking at in terms of a liter of urine? What are we getting out as nitrogen?
Okay, last question here.
Okay, thank you. Keze from University of Yaoundé in Cameroon. My question is equal to the previous question and it has to do with TrueBuy because I'm equally working on it. And I'd like to find out, on the one hand, what you people did with the effluents after the precipitation, and mindful of the fact that obviously it will still contain some nutrients. And secondly, did you consider using a motorized reactor, or was it a hand-stirred reactor? And have you carried out any studies to verify if there is a significant difference when you stir with an engine as well as when you stir with a hand? Thank you.
Okay. Now I can give you the audience if you can answer.
Okay, thank you. The first question is, if I'm not mistaken, about the production rate of struvite and what to do with effluent. The production rate for struvite in our case, in our specific situation, is we precipitated 1 kilogram of struvite from 520 liters of stored brine. So for the question that's related with the effluent, in our case, what we did was we used it as a urea, like nitrogen feeding, I mean the supply of nitrogen, because it is full of nitrogen. So another way, if you don't want to, because it depends on the soil situation. So if the soil is depleted with nitrogen, and then you can use it as an additive that's at the developmental stage of the crop. But if you don't like to use it, or if the soil is rich with nitrogen, and then you can evaporate and you can eat, no problem. So then the other question is about the reactor, how it works. So we used manual steering type, but not motorized one. So because I can't tell you anything about the difference between the two, because we didn't try the motor. So what else? So thank you.
You can chair us for the session. So William.
No time. Great. Okay, I'll be very fast. For Loic, we need a different cation, a different ion exchange resin, because the phosphate is negatively charged and the ammonium is positively charged, so you need a different resin. For the second question, we've been thinking about that as we're evaluating these technologies early on in the development process, but I'll talk to you more about it at our poster.
So, for the questions, so you can join the audience and you can discuss in face-to-face. Thank you all, and I'm very happy to be moderating this session, and so thank you to the organization committee of the FSM3.